I will now discuss the construction methods and technologies our team implemented in the design of our prototype. We knew that the exterior envelope would be a critical component in reducing energy usage. After researching many systems and technologies, we selected structural insulated panels, or SIPs. This method provides the building structure and insulation in a single prefabricated component. Each panel consists of 2 layers of OSB sheathing with a rigid foam insulation between. These panels provide excellent insulation and cut down on material waste dramatically. Here you can see that SIPs easily outperform standard framing. A SIP panel has much greater R value than an equivalently thick stick-built wall, and only allows about 7% as much air infiltration. The thermal image on the bottom right shows the thermal breaks which occur every 16 to 24 inches with standard framing. SIPs can go as far as 20 feet without these thermal breaks occurring whatsoever. The result is a dramatically reduced space heating and cooling loads, which will be exhibited later. Because of the large amount of glass our prototype uses to take advantage of solar gain, it was imperative that we provide windows with excellent thermal properties. Testing various assemblies proved that triple-pane low-E windows provide excellent yearly energy savings. The implementation of green roofs also provided a host of benefits. Green roofs reduce water runoff and heat island effect while protecting the roofing materials. This extends the life of the roof while providing an attractive outdoor space. Our team also developed a set of criteria that should be used while selecting finishing materials. These criteria should be relatively universal and are as follows. Use recycled or naturally abundant materials. Use materials which require less energy to produce. Use materials which do not negatively impact indoor air quality. Use materials which are durable and last longer. And avoid using materials which will end up filling landfills. In addition to these passive strategies, our team considered a number of active systems to either reduce energy usage or to produce energy on site. I will now take some time to explain some of the systems we decided to implement. The use of a geothermal heat pump provided excellent energy savings and a relatively short payback period. This system allows outdoor air to be tempered by the constantly cool temperature of the earth before indoor use. This provides ample cooling in hot months with no need for an air conditioner, and can begin to warm winter air to ease the burden on mechanical heating methods. We choose to implement a vertical loop system, which will disturb less of the site and can be implemented easily in urban areas. Solar thermal, or solar hot water, is another system we found to be quite effective. This system uses heat collected from the sun to heat water for various uses in the home, such as space heating, showers, laundry, etc. This system will be effective even on cloudy days, and a small backup heater may be used to achieve the hottest temperatures on demand or at night. A radiant floor heating system is coupled with the solar hot water system. As you can see from the diagram, radiant heating is far more efficient than forced air. It also provides comfort at lower temperatures because objects are heated directly, not by heated air. Greywater harvesting was also considered for this project as a means to reduce wastewater production. Greywater can come from sources such as washing dishes or showering, and can be filtered and purified quite simply. This allows for this water to be recycled on-site for purposes of landscaping, or simply to be drained naturally rather than being sent into the city sewers. Finally, solar electric panels were used to generate all needed electricity on-site. Rather than storing power on-site, we chose to tie into the local electric grid. This allows the prototype home to buy electricity during peak usage and sell surplus electricity back during times of surplus. Here is a study of the various components needed in a photovoltaic system and their associated cost. It was important that the system be economically viable for potential customers. One of the most expensive components is the grid tie inverter, which we are able to share between units to reduce on cost. We determined that our PV system would provide enough electricity savings to pay for itself in about 11 years, which is less than the estimated life of the components. All in all, we decided this would be a viable solution to our on-site electrical needs. In order to measure our progress, we have compared the performance of our prototype home to that of a hypothetical average home, which was previously mentioned. Here you see a summary of yearly energy usage calculated by an eQuest simulation. For ease of comparison, we have converted all energy usage to kilowatt hours. In the course of a year, we estimate an average home in this area uses nearly 48,000 kilowatt hours to operate essential building systems such as heating, cooling, and lighting. In an identical simulation, our prototype used just over 15,000 kilowatt hours per year per dwelling unit. Our prototype uses no gas and can therefore produce all required energy on site. To review, here is the average home. You can see that space heating and lighting are the largest energy consumers by far. Through efficient design and passive systems, our prototype was able to eliminate about 2/3 of that energy usage. In the prototype, one can see that space heating and lighting are no longer the chief consumers of energy. We suspect energy usage could be driven down further by ensuring the use of Energy Star appliances in the home. The remaining energy required by our prototype can now be provided by on-site solar electricity, reducing our net energy usage to zero. The impact of these energy savings can be appreciated in a number of ways. First of all, huge savings are passed on to the owner of such a home. The owner of our prototype home will use about 1/3 of the energy of his peer in an average home. This results in nearly $3,500 a year in savings. If these savings were reinvested toward the mortgage on the home, the owner could save about $188,000 over the course of a 30-year mortgage. The environmental impact is also easy to appreciate. The amount of energy savings our prototype provides over the average home leads to about 26,500 pounds of coal each year. If implemented on a large scale, this could have profound impacts on the emission of greenhouse gases. Throughout the course of this project, it has become apparent that efficiency is inherent in a multidisciplinary approach, and that through efficiency, sustainability can be achieved. Through sustainable design, we have not only reduced energy consumption, but also reduced infrastructure and cost. By challenging convention, our proposal provides enhanced green space and a sense of community, even at increased density. By working collaboratively, our team was able to create a net zero energy housing prototype.